we will calculate the magnetic field on the axis of a circular current carrying loop, where the current carried will be I and radius of the loop is R, and x is the distance of point from center of loop. That means the point where you have to calculate the field. So the diagram will be like this. This is the current carrying loop, circular current carrying loop. This is the point P where you have to calculate field, and this is the distance x, and this is radius of the loop R, and this is the current I in the loop. So at this point P you have to find field. So for that, what we have to do, we have to choose a very small length dl on the circumference of this loop. So we can choose this dl like this. This is dl. I think you could follow what I have drawn. This is dl, a small part of the circumference, dl, right? Now, so dl, this is the position vector of the point. P from that small length dl, that's it. R, position vector R, and angle between this dl and R is obviously 90 degree. See, it's a three-dimensional diagram. So this angle happens to be 90 degree. Okay, so dl cross R is in which direction? dl cross R is here, this direction. So this is the field dB due to this length dl. So similarly you have a length here also, right? Here the length will be in this way. This will be dl and dl cross R. dl cross R due to this is the direction of the field. Okay, so what happens actually, the resultant value of the magnetic field, the resulted magnetic field is directed parallel to the axis of the loop. So that means if this angle is theta, so this angle is 90 degree minus theta, so this is dB cosine 90 degree minus theta, or dB sine theta. So the total magnetic field X is summation of this dB sine theta. Okay, now what is dB equal to? This was the length dl, R, okay, so dB, what is dB equal to? dB equal to mu naught by 4 pi and I dl sine, so this angle is obviously 90 degree, sine 90 degree divided by R square. I mean this magnitude is R, by R square. So we need to find out this dB sine theta. dB sine theta is mu naught by 4 pi I dl, sine theta will be 1 divided by R square multiplied by, so this is theta, So sin theta is r divided by small r. So if you integrate that, you get bx. So if you sum up this thing, then only you have to add this dl, rest all are constants. So summation of dl will give you the circumference of the loop. So integration of dl is how much? Integral of dl is 2 pi r. So here you have mu 0 by 4 pi I into 2 pi r multiplied by r, so r square, divided by small r cube. Small r cube means small r is then x square plus capital R square to the power 3 by 2. So this is the resultant magnetic field on the axis of the current carrying loop. It is denoted by Bx because it is along the x-axis, that is the axis of the loop. So this Bx you can write like this, mu 0 by 4 pi I 2. So what is this current multiplied by pi r square? That's m, right? M is what? M is I into pi r square. It is the magnetic moment of the loop. We have studied this in previous topic. Magnetic moment of the loop is how much? For a single term loop, it is the current multiplied by the cross section of the loop. So here is the current and the cross section. This radius is r. So I multiplied by pi r square is the magnetic moment of the loop. So this is the formula. Now if it is very very far away, so this is the thing. Current now if if this x is much greater than r, that is for a very very far point, now bx will be approximately mu 0 by 4 pi 2m divided by x cube. Now here the magnetic moment, the direction of the magnetic moment of the loop is which way? This way, na? There it is, direction of magnetic moment of the loop. So this formula reminds us of something. So it is very similar to the field due to the electric dipole. If the electric dipole has a dipole moment P, then at a point on the this is the axial position or the end side position. This is the magnetic field. My electric field is how much? Here is 1 by 4 pi epsilon naught 2p divided by x cube. If this x is much larger than the dipole length, so similar thing happens in case of this magnetic dipole. See, here the similarity between the formulas is like this. There you have the electric dipole moment, here you have the magnetic dipole moment, rest all are same, mu 0 by 4 pi, and here you have 1 by 4 pi epsilon 0. Similarly, as due to this current carrying loop, there is, that is actually equivalent to a bar magnet, you know. This loop, the loop is equivalent to a bar magnet. This is the magnetic moment vector. That means it's like having south pole here and north pole here. And for a bar magnet, the magnetic lines of force due to this current carrying loop and the bar magnet are same, especially for very very far away points. So there it is. It doesn't look like symmetrical now. I'll draw one more diagram. See, here it is. This is the current carrying loop. This is equivalent to a bar magnet. Magnetic moment this way, and these are the magnetic lines of force. Okay, so here at a distance x, here obviously we have found out the field here on the end side position. So again I will write that here the magnetic field is approximately mu 0 by 4 pi 2m by x cube. So here on the perpendicular bisector, the magnetic field is mu 0 by 4 pi m by x cube. Pretty similar to the electric dipole. In electric dipole, what did you have? There at the end side position, the electric field is 1 by 4 pi epsilon naught 2p by x cube, and at the broadside position here field was 1 by 4 pi epsilon naught p by x cube.